To have David Schroeren. He graduated recently from Princeton with the thesis in philosophy of physics, and is now a postdoc at the University of Ginebra. He's part of a funded project on the metaphysics of quantum objects, whose PI is Claudio Cardosi. And then he works mostly in the metaphysics of physics and the general topics in philosophy of physics. And today he's going to talk about the haecceitism and its supposed quantum counterpart, which is the notion of a quantum permutation. So you have about 50 minutes, then we'll have a 10-minute break, and then we'll go with the Q&A. All right?
Perfect.
Do you want me to tell you when we have like 5 minutes?
I will start my timer now, and that should be fine. But maybe if I'm massively running, just give me a sign and I can.
All right.
Thanks so much, Alexandra, and I'm really, really excited to be here. It's a great privilege to present my work. The topic of this talk is an area that is one of the kind of most exciting places where people have been trying to draw out metaphysical conclusions from quantum mechanics, in particular about metaphysics of quantum objects, the name of the project that I'm a part of. And what I want to do today is to put some pressure on what I take to be an underlying premise of this enterprise of drawing out conclusions from quantum mechanics about metaphysics. And that premise, as I will explain in more detail, is that quantum permutations are qualitative isomorphisms, and I don't believe they are. And that has some impact on the kinds of conclusions we can draw. I will show you that some, but not all, conclusions that people have been trying to draw still hold up. So the notion of permutation, and this is kind of what launches this whole project, right? You look at metaphysics and you look at philosophy of physics, and you see these groups of people tend to care about something quite similar, and namely the notion of permutation, right? So take all the objects that exist in some world, all the things that behave sort of syntactically like first order things, and consider the group of permutations of things in that world. Permutation here is just basically an assignment of each thing to some other thing. So take a world in which two things exist, Alex and Sam. Permutation at that world is a map that assigns Alex to Sam and Sam to Alex. It's just a swap of the two. And the group is just, in a sense, a way to systematize talking about bijections like that, talking about ways to map things to one another. This notion of a permutation of objects of the world is something that metaphysicians, of course, care about. Metaphysicians want to know, how does the permutation of objects of the world affect the worlds themselves? What happens to the world if I map things to one another? Metaphysicians capture this notion in terms of the notion of a qualitative isomorphism. To get a grip on what that is, let us suppose for the moment that a world possibility in metaphysics is a kind of maximal proposition, a proposition that implies every proposition that it is logically consistent with. So, for example, take again our world with Alex and Sam, and suppose that the maximal proposition at that world is that Alex is green and Sam is red. Then a qualitative isomorphism is just what happens to that proposition if you replace Alex with Sam. So it is the thing that takes the proposition that Alex is green and Sam is red to the proposition that Alex is red and Sam is green. All you do is you swap Alex for Sam at every place where Alex occurs, and Sam for Alex at every place where Sam occurs. So technically, slightly more precisely, qualitative isomorphism corresponding to some permutation of the objects of that world is a map that takes one world, namely a maximal proposition, to a distinct proposition that differs from the original one merely in a uniform substitution of the objects in the original world according to that permutation. Now, physicists, of course, as I mentioned, and philosophers of physics also care about permutations. They want to know, how does a permutation group of the object at some world act on the physical states of the objects at that world? Now, a state is a little bit just like, it's a little bit something like a maximal truth. We'll get to the bottom of that But later, I'll say more about what a physical state is. It's something quite similar, but not quite the same. In physics, that question is answered in terms of the notion of what I call a quantum permutation. Technically, it's what's called a unitary representation of the permutation group on the Hilbert space of the system, where a Hilbert space is the mathematical object that we use to talk about the physical states. And the representation of the permutation group on that space is just a way to make precise what permutations do to physical states. If these notions don't seem familiar to you right now, don't worry. I'll say a little bit more about them later. And a general note that I should have put right at the beginning, 90% of this talk should be intelligible to everybody. If at some point you feel completely lost, feel free to interrupt, and I'll be happy to try to guide things back on the path. So again, I'll say more about this notion a bit later. It's worth stopping for a moment to think about why metaphysicians, what work metaphysicians do in terms of the notion of qualitative isomorphism. The reason why people care about the question how worlds behave under permutations is because it allows us in metaphysics to articulate certain interesting controversial theses that concern modal metaphysics. Consider the following question. For any possible world, again, we're holding fixed that we think worlds as maximal propositions. For any possible world, is the image of that world under qualitative isomorphism itself a possibility? Haecceistists say yes, and anti-haecceistists say no. That is a way to cash out these two theses in modal metaphysics. And of course, lots of debate has been raging about which of these is true. On the other hand, physicists care about the question how physical states change under permutations, because we have lots of empirical evidence for a certain property of quantum states, namely that they are mapped to themselves under permutations, under quantum permutations, under the quantum implementation of the permutation group, namely the bijections of objects, the map of objects to each other in a given world. And I'll say more about this particular aspect, namely the symmetrization postulate in a moment. Now, as I mentioned earlier, in the literature that tries to draw out metaphysical conclusions from permutation, invariance, and quantum mechanics, it's quite widely presupposed that quantum permutations just are qualitative isomorphisms. That's how we get all these beautiful conclusions that tell us, for example, so there is a recent collection of papers by Oxford philosopher Adam Colton, who says that if we have this kind of symmetry in quantum mechanics, symmetry in permutations, then the question of whether haecceitism is true or anti-haecceitism is true can't even be articulated. The question is trivialized or obviated in some way. And so the goal today is to argue that this identification is mistaken. Just to give you a rough idea for what I will identify as a diagnosis, it's that quantum permutations, the things that modify states, they possibly generate qualitative differences that don't merely concern which object plays which role in a world in the overall qualitative profile of that world, but that concern also the qualitative profile itself. Whereas practically by definition, qualitative isomorphisms don't affect the qualitative profile. They hold that fixed. All that changes is the pattern of instantiation of the qualitative. Here's a quick overview of the plan. I'll quickly clarify some background principles and then explicate some preconditions, some backstory that we need to give to understand those principles. That's section 2. I'll then tell you why I think quantum permutations are not the same thing as qualitative isomorphisms. And then if there is time, I'll say a little bit about why the existence of symmetry under quantum permutations and quantum mechanics does not obviate the question of haecceitism. The literature on permutation invariance implicitly or explicitly presupposes two things. The first thing is that if you talk about an n-particle quantum system, you're actually talking about a system with n constituents, something that is built from n things. Now, just a few clarifications about this. You can think of the constituents basically as the building blocks of the system, as the material things from which the system is built. I will refer to these constituents also following the literature on the topic as particles, but it's worth keeping in mind that this is not supposed to carry any kind of implications about particles necessarily having precise locations. That is not a view that is adopted in the literature of particles. It is adopted by certain views about the interpretation of quantum mechanics, in particular Bohmian mechanics, where it is the case that particles, if there are Bohmian particles, they essentially have precise, exact locations. That is not something that we disclose here. Moreover, it's worth keeping in mind that constituency is not a thesis that in any way decides the question of haecceitism. Just think about the metaphysics of space-time. There are people who are anti-haecceitists and yet think that there are spatial points. They just also believe that you can't actually get a new possibility by commuting. So this is saying that n-particle systems have n constituents does not prejudge in a question-begging way this dispute. It's also not really a thesis about whether particles are individuals for very similar reasons. By elementary constituent, I just mean a constituent of the system that in a sense is rock bottom according to the system. That is among the most fundamental things that are described by the theory. We're leaving open for present purposes whether the quantum mechanics of n-particle systems is also a fundamental theory that is fundamental, kind of unrestrictedly speaking. That is not something we need to settle for other purposes of our talk. The second presupposition of this literature is what Fred Muller and Simon Saunders have called the State Postulate. Basically, there are some symbols in here, but basically the idea is that there is a certain mathematical entity that represents physical states. That entity is called the Hilbert space. And basically what you see is that there is a term in the overall Hilbert space, one for each particle. Right? So you have a way to basically capture the degrees of freedom of each particle, all the possible respects in which a particle can vary from one state to the next. You have one of those things for each particle. It's a bit like in classical mechanics, where you have a way to talk about ways in which each particle can differ with regard to its location and with regard to its velocity. Now, of course, there might, just one more clarification, there might be further restrictions on what the physically possible states of a system are. They might just correspond to a subspace of this Hilbert space, which I've denoted by this tensor product H. For example, you might say only those that have a certain symmetry property are physically possible. Now, if we will get to this kind of restriction later, for present purposes, think of H as describing the states that are possible in the broadest sense, something you might capture calling them the metaphysically possible states. The state postulate straightforwardly raises the question, I mean, what do we mean by the idea, by this notion of each of those factors in the tensor product being associated with a particular particle? I said each of those terms captures the degrees of freedom of a particular particle, but it's not obvious what we mean by that. We're no longer in classical mechanics, and I'll explain to you in a moment why this is extremely non-obvious, what we mean by this. And of course, this has been a major source of debate in the literature on permutation invariance and its metaphysical implications for questions like haecceitism. So we would like to know what is meant by this. We would like to understand what we mean when we say a particular factor in the space belongs to some particle. To answer this question, we got to do a bit of work by way of preparation. First thing we'd like to know is what is the ontological category of a state. This isn't supposed to be some kind of question about we're now adding something to the ontology, but we're just like, what are we saying when we attribute a state to a system? What is the kind of thing we're expressing when we say that a system or two particles or three particles are in a given physical state? There is some evidence that we get from just seeing how we talk about states. I've already been using this language in this talk. We say things like n particles are in a particular state, or n particles instantiate some state. This language suggests that states are the kinds of things that are properties of these collections of particles. Think back to our case of the world consisting of Alex and Sam. We might say when the maximal truth is such that Alex is green and Sam is red, then the collection Alex and Sam instantiate a certain state, namely the property of being red and green. in a sense, you can think of states in that way. It's not supposed to be kind of an additional heavy-duty metaphysical assumption. It's just a kind of personification of what we do when we attribute things to collections of particles by attributing to them a state. So states are, on this picture, of the type inhabit property. It's the kind of thing that combines with n things, n individuals to form a proposition. And those propositions that attribute states to particles is something I will call a state proposition, and which allows us to kind of write a state proposition in this kind of subject-predicate form. And so if you have n things, label them A1 to AN, and you have an n particle state, then to say that the n things are in this state is just to state this truth, to express this state proposition. Everybody with me so far? All right, great. Now, we're familiar with the idea that we can build, so we have, of course, single particle states. I can tell you what state a single particle is in. I can tell you what state another single particle is in. And that means I can tell you what two particles are in, right? By having told you something about the single particle states. So there is a way we can build multi-particle states from single particle states. And that's something we know already from classical mechanics. Classical mechanics, we know that a single particle state is something that attributes a particular position to a particle and a particular velocity to that particle. That attribution is an attribution of a monadic property to the particle in this state, right? In this way of thinking about it, that state is instantiated by a particular particle. It's the kind of thing that possibly is instantiated by some particular particle. Now ask, what is a classical two-particle state? It's the kind of thing that assigns a particular position to one particle and a velocity to that particle, and it assigns another position and another velocity to the other particle. So in a sense, what we're doing when we build a two-particle state out of a single-particle state, we do something like logical conjunction. And for those interested in the kind of conjunction I have in mind, it's something like property conjunction. Here is how you can write it down slightly more formally. We can talk about it later if you have more questions about the technical detail here. And of course, that means that in this general scheme of thinking of states as properties, two-particle states are dyadic properties, and more generally, an n-particle state is the result of conjoining n single-particle states, or two n divided by two adic states, as it were. That's the basic idea. So the conjunction is a kind of state as a property-forming operation that takes a k adic property and a k prime adic property and outputs a k plus k prime adic property. Now, in quantum mechanics, the hair on the soup is that we have another way to build states out of other states. We have something like conjunction, but we also have something else. The conjunctive operation is, in the formulas of quantum mechanics, represented by what's known as the tensor product. Here's an example. Take two single particle states. Now we're going to move a little bit into the quantum notation where states are represented by these Greek letters, phi in this case and phi prime. Take two single particle states, phi and phi prime, then the tensor product of the two is going to be a two particle state. So the tensor product here, you can think of a little bit like a logical conjunction, though there will be a big caveat to that in a moment. The other operation we have is known as linear combination, and that's not something that takes you from a property of one adicity to a property of higher adicity. It takes it from a property of a given adicity to properties of the same adicity. It's basically, in classical mechanics, all you could do is, in a sense, logically conjoin states. Now we can add them and subtract them and multiply them. Right? That's what linear combination does. It's a bit like you're now in a vector space. Previously, you weren't in a vector space. Right? That's really all you need to know about what linear combination is. And the second thing you need to know is that if I linearly combine two things, I am not getting a different adic state. I'm getting a state of the same adicity. Here is the hair in the soup. The linear combination operation does not mesh with the logical conjunction operation, the one that we in quantum mechanics implement using the tensor product. There is a technical term for quantum states where tensor product does, we can think of it as just a logical conjunction. That means there are quantum states that just are logical conjunctions of single particle states. Those are known as the factorizable states. Those are the states that essentially, if you look at them, they are just tensor products of single particle states. That's it. But there are also, of course, lots of other states that are not factorizable, that are linear combinations of factorizable states. And those you can't think of as just logical conjunctions of single particle states, because linear combination, once you've linearly combined, you no longer have that kind of connection. Here is an example. You have two single particle states. In fact, so the phi's are supposed to be in the Hilbert space corresponding to one particle and the psi's in the other. You put them together in this way, where we have here we have a two-particle state. Here we have another two-particle state, and now we add them, and we have something that's also a two-particle state, but it's no longer, you can no longer look at it as a logical conjunction of those steps, precisely because there is a plus in the middle. Plus messes it up. And this means basically that there are certain ways, and so now return to our question. I want to find out what it is for a particular particle to be associated with or to belong to some other space. Here is why we wanted to know this. Remember, the state postulate, according to Fred Muller and Simon Saunders, talks about this idea that we have this association. What we just saw, that that linear combination doesn't match with logical conjunction, means that a straightforward, kind of classically tempting idea for cashing out what it is for a particle to be associated with a particular Hilbert space just doesn't work. In classical mechanics, we saw that basically for every state of the n single particle, for every state of the n particle system, there are n single particle states, such that being in that n particle state just is for each particle to be one of those single particle states. That is kind of the logically conjunctive nature of classical states. So you might have the classical idea that for a particle, now back to the quantum setting, right? For a particle to belong to some single particle Hilbert space, just is for it to be the case that at every time there is some single particle state from that space that the particle instantiates. But of course that's not true, because if you go back to the case of this kind of superposition of the linear combination states, it's not true that if the two particles are in the superposition, one of the particles will instantiate any of the single particle states that the superposition is built from, that the linear combination is built from. Basically, the idea is sunk by the ubiquity of non-factorizable states. If all we had were factorizable states, we could use that idea, but we can't. So this idea, just to draw the line from this conclusion, is sunk because you can have a system of n particles, right? And throughout its history, none of the particles ever instantiates a single particle state. They could stay in a non-factorizable state throughout their entire history. Right? So you can't cash out what it is for a particle to belong to one of those single particle states by saying it always has, or even you can't even say at some point it will have one of those single particle states, right? Because it might never have, and generally will never instantiate a particular single particle state. And this might lead you to considering a different strategy, which I call the essentialist strategy. Now you say, okay, fine, no particle, it might be true that no particle ever instantiates a single particle state, but maybe all we need is to kind of have a kind of essential necessary connection where if there was ever a case when if there was ever a situation where it did instantiate a single particle state, it would have to be the state from that particular single particle Hilbert space. So the idea is kind of to lay down a rigid essentialist, in the old modal sense of the word, connection between particles and single particle Hilbert spaces. So suppose, for example, here's a way to illustrate it, again, our examples. On this idea, the principle, the thesis would be a particle, in this case call it Sam, belongs to some Hilbert space H, and we're going to call it Sam's Hilbert space, just in case necessarily whenever a particle instantiates a state in Sam's Hilbert space, that particle is Sam. Right? So that means, for example, go to some world where anything instantiates the single particle state from Sam's Hilbert space. This principle says for those to be associated with each other, it's going to be the case that in that world, in that possibility, that particle has got to be Sam. So in a sense, it's an essential truth about the single particle Hilbert spaces. Of course, that's bad because we want to keep an open question in this setup whether haecceitism is true. On this strategy, though, haecceitism is going to be automatically false because you can never, once you have, for example, a pattern fact about n particles being in a certain n particle state, you can't just permute them because basically you're prohibited from having a situation in which a certain single particle state is instantiated by a particle that doesn't belong to that single particle state. So again, we want to keep haecceitism open, so the essentialist strategy is banned. Everybody still with me so far? Great. So a better way, I submit, to explain what we mean when we say a single particle is associated with a Hilbert space is we cache it out in a kind of alignment of argument places with the factors in the tensor product. I want to just illustrate the idea. Got to write in this. So the basic idea is as follows: we have the state in this kind of, say, a two-particle Hilbert space, and we have two particles, A and B. And suppose that at some instant of time, the state proposition is true, so that A and B are in this state. What is it? And we've not said anything about whether it's factorizable or not. It doesn't matter. What is it for A to belong to H1 and for B to belong to H2? Well, A is the first argument place, and H1 is the first term in the tensor product, and B is the second argument place, and H2 is the second term of the tensor product, right? That's all there is to belonging, right? That's the basic idea. Here is basically explained on the slides. So again, recall at every instant of time, basically we have some such state proposition that is true, right? That's an underlying idea from that's kind of essential to a state. And so we cache it out in terms of this alignment of argument places, order and argument places with order in the tensor product. So take an n particle system, use the idea in slightly more general terms. Then with the state space that is an n full tensor product of H1 to Hn. Then for some particle B to belong to the kth factor in this tensor product, Hk, it's relatively the case that any physical state represented by some vector in this overall Hilbert space, the kth argument is identical to B, just in case this state proposition is true. That is a slightly more precise way to put this basic idea that I explained to you before. Again, just to give you some examples so that you're more familiar with this idea. If S is a factorizable state, then some particle B belongs to Hk just in case B instantiates some state in Hk. So we're going to have the classical strategy back for factorizable states. It collapses to the classical strategy. But it also works for non-factorizable states, basically for the reasons I explained up there. Now, this way of thinking about what it is for a particle to be associated with a particular factor in the overall tensor product allows us to put particle labels on particular factors in the Hilbert spaces, in the terms in the overall Hilbert space, tensor product Hilbert space. Here is how. Consider again a two-particle system. So we have two particles, A and B, and the joint state space is given by this tensor product, H and H prime. So for the moment, we are omitting any kind of label of them. So we just have two factors, knowing that they each capture some degrees of freedom of the constituents. We have, suppose also we know that A belongs to H and B belongs to H prime. What does that mean according to our account? It just means that there is some state proposition that is of the form SAB, so that A is the first argument and B is the second argument. That's what it is for A to belong to H and for B to belong to H prime. Now, in this kind of way of thinking about it, we're, for the sake of clarity, we're holding fixed the order of the Hilbert spaces, and we're just kind of looking at what happens when we when we do things to the arguments. Now, this fact about belonging in this case, we can express by putting labels on the Hilbert spaces. Right? So if A belongs to H and B belongs to H prime, we can relabel H as HA and B and H prime as HB. That's the underlying idea. It's fine with a couple of seconds here. Now, the important thing to realize here and to highlight is that these labels don't function like names. Remember, at least according to Kripke orthodoxy, names are rigid, so pick up the same thing at every possibility. This is not the case for Hilbert space labels. Hilbert space labels are contingent. They depend only on the alignment of the order of the tensor product with the order of the argument places of states that are instantiated by constituents of the system. And of course, these things can change from one world to the next. At least if it can change from maximal propositions to maximal propositions. I can try to keep open whether these propositions are possible worlds and to not prejudge the question of haecceitism. For example, suppose that instead of SAB, which licenses the idea that H is HA and H prime is HB, instead of SAB, instead there is a possibility where SBA is true. In that case, we would come to a different conclusion about what labels to put on those Hilbert spaces. That's just where we have set up. The idea that states are their properties, just as a matter of notation, licenses treating vectors kind of as predicates for an n particle system, n-adic predicates. So in a slight abuse of notation, I will write. I might have gone too quickly here. Right, so this is what you're supposed to see. So this is just the generic Hilbert space vector, the kind of thing that represents a state, the dyadic property for a two-particle state, and its state proposition is just something you express on this notation in terms of this predicate, object-predicate format. Now we can get to the juicy bit where we find out whether quantum permutations are in fact the same thing as qualitative isomorphisms. You already know what I will tell you, namely that the answer is no. To begin with, we can use this machinery to tighten our understanding of what a qualitative isomorphism is in this setting, what it does. We already saw a kind of rough and ready introduction earlier, but here is a slightly more precise version of this idea. Again, we're going to consider a two-particle system with two things A and B, and a permutation that just takes A to B and B to A. Alex to Sam and Sam to Alex. Further, suppose that state proposition SAB is true at some instant of time, a proposition that assigns two particle state S to the things A and B. We can then ask, how does the permutation that swaps A and B, what does that do to the state proposition SAB? The answer should be clear. It just replaces every occurrence of A with an occurrence of B, and every occurrence of B with an occurrence of A. This is what it does. And that's just a slight specification of the answer, and I'm just giving the label again for definiteness to distinguish it from a quantum permutation. Qualitative isomorphisms act on propositions, quantum permutations don't. We'll see that in a second. It is a specification of the earlier idea that a qualitative isomorphism just corresponds to a uniform replacement of particles and state propositions. Now, the next thing we want to know is how do people define quantum permutations? And here, just as a warning, I will have to delve a little bit into the notation from the literature. I will do not beg the question. I'm just basically copying Butterfield and Colton's definition of a unitary representation of a permutation group, so that we can see exactly what's going on, how the labels match up and everything. If you don't follow along in some parts of the slide, you should be back up to speed at the end of it. That will be a nice example to tell you what's going on. So the goal is to define what's called a unitary representation of the permutation group on Hilbert space. That's basically just a way to say what the permutation group does to states that preserves the overall structure of Hilbert space. in particular, that preserves the length of states, so that it's the kind of quantity that we use to make predictions. So we don't want symmetries to change the length of the helpless space vector, because they will change our predictions. Right? So that's why we use a unitary representation. And here is how we specify one. The first step is to specify how permutations act on a certain special range of factorizable states. Those special factorizable states are called the basis vectors. Basically, those are the ones that if you linearly combine them with one another, you can recover all the states in the whole space. So take, again, a system of two particles, and suppose that we have Hilbert space HA that we are just going to take for granted is associated with A, and HB that is associated with B. We're forgetting for the moment about my particular account of what this association consists in. We're just going to follow Butterfield and Horton here. And they each have their own dimension. That means that there is a certain, in a sense, a certain size of the basis that you need to recover everything in the Hilbert space. And then you have the basis vectors themselves. As you can see, they're just tensor products of, in this case, single particle states. The subscripts basically range over the dimension, so that you catch all the, or you can linearly combine them to recover all the states in the overall tensor product of the space. And so here is the kind of base case of how a permutation acts on, according to Butterfield and Horton, acts on one of those vectors. What we do is we take the basis vector on the left, and we basically swap around. We swap around the size of the tensor product, while also changing the particle labels. So A stays on the left and B stays on the right. All we change is now we say, well, previously A was in psi, it is now in eta, and where previously B was in eta, it now is in psi. That's the basic idea. And the second thing we do, the next step, so it's kind of the base case, right? I tell you how the basis vector behaves under a permutation, and then I tell you how every other state in the Hilbert space behaves under a permutation.
Sorry, David, for these to work, then HA and HB have to, I mean, I don't understand what does it mean, for example, eta J of A, if eta was a state in HB. So how do you identify this state, this vector which was in HB with one in HA? How does that identification work?
Well, the idea is that that there is a kind of a very similar state in HA, and that you kind of.
So HA and HB have to be.
No, wait. What you're doing is you're basically saying you're swapping around which Hilbert spaces they have.
Yeah, because you can allow for
exactly
HB
right.
different dimensions.
Right. So you're basically saying so this is defined on arbitrary, not necessarily indistinguishable particles, right?
Mm-hmm. But then, for example, if HA contains particles with some property, for example, charge, HB is particles without that property, then when you interchange them, then suddenly B has charge and A doesn't.
That's right.
Okay.
Right. That's got to be the idea, because as right. I mean, I think the reason why it feels strange is that we normally see these defined for similar particles that share all the quantum numbers. But of course, you can do this for distinguishable particles as well that don't share the same quantum numbers, in which case that's exactly what happens.
Right.
Right, so the first thing we've done is we have specified what happens to basis vectors, and then we say what happens to any vector that you might obtain by linearly combining basis vectors. So that's what happens when you extend by linearity. the basic lesson is, once I've told you what happens to basis vectors, I know what happens to any vector. The rule is basically written like this. That's just the extension by linearity kind of description. It basically says the permutation of a linear combination is equal to the linear combination of the permutation. That's the definition that you get. Now, if this was a lot, here is basically a more simple example. Take this non-factorizable state of particles that are both similar, so they share the same quantum number, and they're in this non-factorizable state. What happens to them under a unitary action of the permutation group, what I call a quantum permutation? Well, it's just this. You swap the two sides of the tensor product, and you maintain that the left side of the tensor product is the state belonging to particle A, and the right side of the tensor product is the state belonging to particle B. Now, the first thing to note is that quantum permutations of factorizable states are qualitative isomorphisms. And to show this, there is a kind of recourse to the conjunctive nature of it that we will need. I have 10 minutes. I'm going to try to, I think actually, basically at the core part, just a moment, so that you find. Take a two-particle system that is in this factorizable state. A has spin up in some direction and B has spin down in that direction. When we're thinking about single particle states as corresponding to monadic properties, so suppose that spin up is F, property of being F, and some F, and spin down is G. Basically, then you can write the state proposition as jumping the gun a little bit here. Just back up a little bit. What happens when you do a qualitative isomorphism on the state proposition? The state proposition that assigns this factorizable state to A and B. It is just a replacement of A with B. That's something we saw earlier. Note that we're also replacing subscripts because that's how the subscripts are defined. It's just a matter of which location in the arguments these particles occupy. Now, factorizable states are just conjunctions of atomic single particle state attributions. Now comes the idea that I expressed a moment ago, namely, which we saw at the beginning, single particle states are monadic properties. Take the idea that spin up corresponds to F and spin down corresponds to G, then this state proposition can be abstractly formulated as this conjunction. I'm just using different symbols here to make clear that we're now using this re-expression of the tensor product for factorizable states in terms of the conjunction. Now we use the commutative property of conjunction to get this. Hang on, there's something fishy here. Okay, I'm confused now. I feel like this should be, I need to swap around the B's and A's as well, right? Definitely. So, let me try to do this. Basic idea, which I'm currently a little bit, I'm not built in a mistake in these slides. The basic idea is that you can swap around. Logical conjunction is commutative, and so basically what you get is something that is right to G with F A B B A, which so this is basically F A. This is G B F A, and this is right exactly. That's the idea. Yeah. Oh, yeah? What the people don't see. Oh, they don't see this? Nothing soon. Okay, what do you need to do now? Yes, sir. Oh, but I'm not varying anything. I mean, yeah. Oh, I should, yeah, so do this. Like that? Okay, just so forget about the slide for a second. The idea is just, can everybody see this now? In Zoom? I think you want to look at that little window there. Yeah. Now. Yes. Yeah. The line. Well, we need to launch a presentation. Right. So basically, the idea is this. So the qualitative isomorphism is the thing that replaces, that just swaps around DNA. And now start with the original state before you do the qualitative isomorphism. And you can basically go from this is just, so forget about this for a second. That just means that A is F and G is B. And given the commutative property of conjunction, this is G is B and F is A. And this just means that, now this should be the other way around. To be A. Okay. So now we have, and now if we go back to writing it in terms of the vectors, you have exactly the same thing as the output of a qualitative isomorphism. That is the idea. What is the upshot? 4 factorizable states, those that can be written as conjunctions. You have exactly the same impact, the same output if you do a quantum permutation, which is the plot of number 2 signs, and a qualitative isomorphism. Let me plug in that view. Oh, yes. Forward analysis. Are we back on? In that few minutes. So there's analytical. Really. There it is. Oh yeah, it's appearing. All right, so here comes the big moment. Yes. Thank you very much. Now, the basic upshot, and this is going to be a slightly complex slide, the basic upshot is that the same thing is true for non-factorizable states. So consider this non-factorizable state. What does a quantum permutation do to it? Well, again, it changes, it kind of swaps around the size of the tensor product to output this state. So previously A was spin up. So the first term, right, A was spin up, and now the first term it is spin down, and so on and so forth. That's what the quantum permutation does. That's the action of the quantum permutation on that state. Now recall that if 2 particles are in this state, then this means that the state proposition expressed by this sentence is true at some instant of time, being labeled at. And if they're in state 2, then at some instant of time, this state proposition the one labeled hashtag. Now the question is, so we have 2 states that are related by quantum permutation. The big question is, are they also related by a qualitative isomorphism? Does a qualitative isomorphism do the same thing? The answer is no. We can investigate this by asking, what is the image of the state at under a qualitative isomorphism? It is just this one, where every occurrence of A has been replaced by B, and every occurrence of B has been replaced by A. And of course, so the crucial observation here is that these are not equivalent. this expression is not equivalent to the hashtag sentence. There is no way you can go just using the truth functional operations from hashtag to this sentence. But this would have to be the case if qualitative isomorphisms were the same thing as quantum permutations. Here is a different way to see the same thing. If you look at that and if you look at hashtag, they possibly differ qualitatively. That very much depends on what C is. If C is the same state, but C needn't be the same. Of course, there would not be a symmetric state, but of course, whether it's a symmetric state doesn't matter for assessing whether these two operations are the same, because as we just discussed with Elias, there are lots of states which are not symmetric, much less that all states are states of identical particles or indistinguishable particles. The tapestry of possible quantum states is much wider than merely the symmetric ones. So this is really the crucial bit where we see that we have a certain action of a quantum permutation on a particular state whose output is different from the corresponding action of performing a qualitative isomorphism. The diagnosis here is that the problem originates in a failure of truth functionality of linear combination. Linear combination messes things up. If we didn't have it, we would be able to treat any quantum state as a logical conjunction. And so, in a sense, the upshot is that extending by linearity is not something that is metaphysically innocent. That's where the correspondence breaks down between qualitative isomorphisms and quantum permutations. Now, I know I'm over time, but maybe if I just take 4 more minutes to just quickly show you one respect in which this has an impact on what people are trying to say about haecceitism. Now, here is the symmetry principle. Basically, the symmetry principle says any physically possible quantum state is mapped to itself under quantum permutations. To begin with, there are two kinds of states. There are the fully symmetrized ones, where the vector that represents the state is mapped to itself, and then there are the fully anti-symmetrized ones, the fermionic ones, that are mapped to themselves up to an overall factor of -1, possibly. And both of those states, the rays they correspond to, are indifferent, of course, to these factors. So both the fully symmetrized and anti-symmetrized states are mapped to themselves under quantum permutations. Here are two examples. For the symmetrized state, swap around the two sides of the tensor product, you get the same state back. Second one, swap around the two sides of the tensor product, you get minus that vector back. Why is this important? Because we have overwhelming evidence that the physically possible states are fully symmetrized or fully anti-symmetrized, which means that the physically possible states are mapped to themselves under all quantum permutations. That is the principle called the Similation Postulate, and there is a lot of empirical evidence for this principle. So we have good reason to think that it is true. And people sometimes claim that there is lots of this principle has lots of implications. So here it's Adam Colton. We've given SP basically the dispute between haecceitis and anti-haecceitis is trivialized or cannot even be articulated. And just to remind you what haecceitism and anti-haecceitism is, as we've specified it, as we've expressed it earlier, the question was, for any possible world, W, is the image of W under any qualitative isomorphism itself a metaphysical possibility? Haecceitis say yes, anti-haecceitis say no. And let's take a look at how Colton conceives of haecceitism and anti-haecceitism for this to be trivialized, for this to be trivialized. Colton begins by defining what he calls an orbit of a Hilbert space vector under permutations. It is just all the vectors that are related to this original vector by a quantum permutation. So you can move around Hilbert space along the quantum permutations and collect all those vectors, and that's your orbit of a particular vector. And then Colton considers two claims corresponding to the orbit that you can formulate. The first thing I call orbit distinctness, which says that distinct elements in the orbit of some Hilbert space vector psi under permutations, distinct elements that differ merely by an overall phase, represent distinct physical states. So here is an example, already up there. That's an example of a state which is not symmetrized, so it's not mapped to itself under a permutation. Its image under a permutation differs from itself by more than an overall phase. So orbit distinctness says these are distinct states. Orbit sameness is just the claim that distinct elements in the orbit of some Hilbert space vector on permutations all represent the same physical state. Now, according to Colton, haecceitism is orbit distinctness, and anti-haecceitism is orbit sameness. And that's the basis for Colton's claim is basically something correct. Namely that once we have imposed the requirement that all states are symmetrized, fully symmetrized, or fully anti-symmetrized, both orbit distinctness and orbit sameness agree. Precisely because they yield the same verdict about which vectors are distinct, represent distinct states, and which vectors represent the same state. Because the only members of an orbit are things that differ at most by an overall phase. So orbit distinctness judges them all to represent the same state. But of course, so does orbit sameness. So if orbit distinctness and orbit sameness are correct ways to capture haecceitism and anti-haecceitism, then Colton is right. But as you might suspect at this point, they are not good formulations of haecceitism and anti-haecceitism. So this was supposed to come up first. Start here now. So these are again Colton's principles. Orbit distinctness and orbit sameness, according to Colton, they concern the behavior of states under quantum permutations. Remember that an orbit is defined basically as a set of vectors that are related to each other to some particular vector by a quantum permutation. But we know, at least if I'm right, we've seen that quantum permutations are not qualitative isomorphisms. So what happens to orbit distinctness and orbit sameness, given SP, is beside the point for the question of haecceitism. We can illustrate this using the case of an n-particle system. Take a state S that is a fully symmetrized state, and suppose that the n-particles instantiate that state at some time. Now, to say that S is fully symmetrized is just to say that S has a certain behavior under quantum permutations. What behavior? It's mapped to itself under all quantum permutations. Of course, that doesn't settle anti-haecceitism, which implies that at most one of those two state propositions is true. State propositions that differ merely by a qualitative isomorphism. In this one, you have the kind of ascending order of A1 to AN, and here you've swapped A2 and A1. According to anti-haecceitism, at most one of those two state propositions are possible. Of course, to say that S is fully symmetrized doesn't settle this. That's just a way to illustrate that we are kind of missing the point when we look at quantum permutations to assess the truth of anti-haecceitism and haecceitism. So the upshot here is, and that's coming to the conclusion, the upshot is that permutation invariance in quantum mechanics does not trivialize the dispute between haecceists and anti-haecceists. It doesn't mean that it doesn't tell us, given certain presuppositions, something about, especially whether haecceitism is true, but it's not something that we can no longer express given the symmetrization postulate. What I've not talked about in this talk is the impact of our results on later questions concerning whether particles, or something to call, have individuality, or whether they are individuals, or whether quantum mechanics is compatible with the principle of the identity of indiscernibles, even though I think quite similar results will hold in those settings as well. That's the end of my talk. Thanks so much for listening.
Okay, so we're going to take a 5-minute break since it went a bit over time, and then we'll take care of the Q&A. Okay? La edad del menos.
Producir más rápido de va a haber seminario de universidad. ¿Cuándo?
Elias, bueno, tú puedes empezar.
Yep. Okay, so thanks again for the talk. My question has to do with how you, the recipe that you give for these qualitative isomorphisms. And the worry that I have is that the result of applying one of those is highly dependent on notation, of how you decided to write the state. So, for example, you wrote the state, including sub-indices for each of the component states, and then at the end you write this AB. And if you leave out these subscripts, then you would get a different result, something like that. I don't know if and I don't know if I understood exactly what you have in mind, but it seems to me that that could be a problem.
So where was it the appearance of the subscripts that was a bit...
For example, if you leave out the subscripts, then it seems to me that you would get a different result, which this recipe of just swapping A's for B's.
I didn't want to create that impression. Really, the subscripts I introduced to create a kind of proximity to the usual notation of a state, which has subscripts, and which also sometimes are just useful as a way of like summing up states, right? But really, that's not needed to understand, at least not to understand the notion of a qualitative isomorphism. For that, all we need to, well, I would say to realize, because that's a fact, not without making the question, all we need to just kind of understand for this is that we look at states, for example, for a two-particle system, as dyadic properties, so the kinds of things that can be instantiated by two things to form a proposition. And for that, it doesn't matter what labels I give the states.
The complete question is, if I leave out the subscripts, is the result of applying one of these isomorphisms the same or not? Does the result of applying the recipe...
Because in the sense that the subscripts are there just ways to reflect this kind of idea that they're ways to reflect an alignment between the order of terms in the tensor product with orders in the argument places of states, which you don't need to, like, if you don't put those indices on there, it doesn't change facts about this alignment.
Okay, I don't know, I'm confused. We can talk about it later. So I have another quick, just general comment. We were talking a bit about it out here, but a word that I have about any of these projects of deriving metaphysical conclusions from quantum mechanics is that, first of all, the standard interpretation, we know that it has important conceptual problems. So, say, why would you take this defective theory at the conceptual level to derive metaphysical conclusions? And the related worry is also saying, we know that these non-relativistic systems of particles are just an approximation to quantum field theory, which we know is much more fundamental. So, I don't know, what do you think about this?
Thank you. Look, you're totally right. I'm not going to disagree with any of that. In a sense, one way to look at this is like people have been engaging in this enterprise of extracting metaphysical conclusions from standard quantum mechanics. Don't ask me why. I probably would have chosen something else. I would have probably chosen something as beautifully well defined as Brownian mechanics, where we know what we're talking about. I mean, here, in a sense, that's an attempt to say, okay, let me go along with your presuppositions about the kind of setting within quantum mechanics that you use. Do the conclusions actually hold? I'm not so sure, is the bottom line, right? And another domain, of course, is the whole indeterminacy debate, where similar framework is usually presupposed. The wisdom of that, I'm not convinced by, but that's what people have been doing. And of course, with your second point, you're also totally right. There is little reason to think that even if you do come up with a precise ontological framework for this messy standard quantum mechanics setting, very little reason to think that that's exactly what the world is going to be like at the end of physics or even at present physics. So 100% granted.
Right, thanks.
Okay, the next one in line is Sarah.
Yeah, thank you very much. So I would like to ask you about the reasons for eliminating as a possibility so what you call essentialism. So it's not clear to me what the dialectic is. So what dialectically, what allows you to rule out this possibility? Because you want it all. What I want is to have a conclusion at the end that is able to decide between these two possibilities. If I go for one, then there is no such a possibility. But it seems to me that the haecceitis will end up saying, okay, here are the set of fundamental things that we have to postulate for a system. According to your view, the set of fundamental things is just the particles. And then we have the state. And if I was able to follow, it seems to me that the haecceitis would say no. And it has to be something along the lines of this essentialist way, because look what we have. So we have a qualitative difference. So the sort of things that we postulate at the fundamental place is not just the particle, but also the state associated to each particle, something like that.
Do you mean that's what the anti-haecceitis would want to say?
No, that's what the the anti-haecceitis would want to.
So the anti-haecceitis would want to go in for a pretty rigid association of exactly that kind of your point, right? So the anti-haecceitis might turn out to be the essentialist I have in mind, right? For example. I think that's right. I think the worry that I have, so in a sense what I'm saying is not incompatible with there being a further fact about the essence of Hilbert's statement. My worry is just when we look at something that is as basic as the association that we're talking about, that occurs in the state postulate, and we're trying to kind of see whether features of quantum mechanics already obviate or trivialize the dispute between haecceitis and anti-haecceitis, or whether permutation variance clearly tells us that one of them is true rather than the other. We should first set up our metaphysical presuppositions in a way that doesn't immediately settle it. Right? So in a sense, so both your call, right? And I'm telling you, look, what you said about haecceitism and anti-haecceitism is incorrect, right? It doesn't obviate it. And I tell you, oh, by the way, my view implies that anti-haecceitism. I think Holden would say, well, of course, it settles it if you build it into the theory. Right? I don't think it would be there wouldn't be a dialectical advance against the person like Holden who thinks that the simulation postulate tells us there is no difference between haecceitism and anti-haecceitism.
Isn't it in the spirit of the original debate? So, look, there's no qualitative difference. There's nothing that's going to make a qualitative difference. And nonetheless, there's this other factors that we can switch A and B, no qualitative difference whatsoever. In the anti-haecceitis, the idea,
yes,
I am not an expert, but what I took to be the view of the anti-haecceitism is no. I mean, there's nothing in there. So the anti-haecceitis is going to say, well, look, this is my view. This is what motivates my anti-haecceitis position. I understand the way in which you set up the discussion, but my motivation is like, there is no alternative work if there is no qualitative difference there.
Right, so that's interesting. So the idea is that the anti-haecceitis will already want to understand. That's the important, in the sense of what you're saying, that's the important bit for the anti-haecceitis, to think of the association already in anti-haecceitis terms. I think that's interesting. I think it would certainly be interesting to, and yeah, I mean, the things, even for the anti-haecceitis, might be interesting to understand a way in which you can spell out this association without already imposing your anti-haecceitis constraint. But I think the basic point is definitely worth a thought whether this setup, given the strong anti-haecceitis impulse that some might have, is already something that they would get a thought. Thank you.
Then we have Oliver.
Hi, thank you. How's the audio there for you, just out of interest? Clear? Good. I thought this was a great talk. It was incredibly clear, and I understood more of it than I expected to when I saw the abstract. So that's great. I just thought, given that, I'd just like to ask a very basic sort of clarificatory question. So the way haecceitism was originally motivated, right, was like, as you know, if a possible world is like a complete representation of the way the world could have been. And the reason that one should obviously be a haecceitis about certain kinds of things is because when I introduce a possible world, a way the world could have been for the sake of argument or for consideration, I can just stipulate in the case of certain middle-sized objects that I'm talking about those things in that world, right? So if I say, if David had missed his flight, he wouldn't have got here by Thursday. To me, it's absurd for a philosopher to come up to me and say, well, what do you mean, David? Well, the answer is, I know I'm talking about David, right? I stipulated that I'm talking about David, and that was sort of Kripke's original common sense motivation for this view. And of course, it's just that Kaplan talked about it with this fancy thing of switching things and worlds. I'm just wondering, can the debate be stated in anything like those terms? Is it because you've just done such a great job of showing us your notation, and when it contains variables and things like that, which are obviously relevant to whether one can talk about another world in this way. I'm just wondering if, this debate or some aspects of this debate can be stated in terms of the original characterization of it.
Just I'm following correctly, the way you were presenting the motivations for haecceitism is that I can make a claim about what would have happened if I had missed the flight, and so what would have happened if Sam had missed the flight, and be certain that I'm still talking about Sam, despite the fact that Sam, in that possibility I'm considering, is not is instantiating a different qualitative pattern, which is that as well? I feel like I'm not entirely sure I'm 100% on understanding that motivation, because presumably the motivation for haecceitism is the scenarios we're considering. That sounds more like motivation for saying I could have existed even. So I'm not a world-bound thing. But the motivation for haecceitism seems to concern also things that are qualitatively indistinguishable, and saying that there are certain scenarios that are distinct, despite there being no way in which I could discern them. But me having missed the flight, of course, is a very discernible situation. So I feel like my sense was that the key motivation for haecceitism was the unwillingness to impose modal constraints that, for example, the kind that the anti-haecceitis imposes, something like an essentialist principle or just a necessary truth that ties individuals to their qualitative roles. But maybe there is another motivation. I'm not entirely sure. Can you say more about what? Maybe that's already helpful as motivation, but let me know what you think.
I guess I would just thought for a broader audience, if there was since you've already worked so hard to make this so clear, it'd just be interested to look at some of your notation and explain to us, for those of us that aren't in the philosophy of physics aspect of this, a debate about the sort of its semantic flavor and exactly what is forcing the, because I think it's to do with the properties of the linear combination in the tensor product that's generating the problem for your opponents, right? So I just want, if you could just walk us through some of that notation a bit so we can see sort of semantically how it's working. Because I always sort of thought for middle-sized objects, I have no idea what to say about quantum phenomena. But I thought for middle-sized objects, sort of part of the motivation for haecceitism is semantic, right? Is that I can stipulate who I'm talking about. You know, I know who Nixon is, and I can say that I'm referring to him in another possible world. So I'm just wondering, with the notation that's good, if you can help sort of enlighten us.
We're all kind of, I guess, on board with the idea that with the idea of what it is to kind of swap around individuals. It's like the underlying idea is that there are these bare things that have no essential properties, and I could have been a poached egg. By that I just mean there is another possibility in which the individual that actually has all my qualitative properties has all the qualitative properties that a poached egg would have. That's the kind of idea behind haecceitistic difference. And people who are anti-haecceitic say, no, that's crazy. Of course I couldn't have been a poached egg or something, because I'm essentially, the response is I'm essentially human, right? Now that's in a sense, that's what a qualitative isomorphism does. What does the other thing do? In a sense, the qualitative isomorphism swaps around things in the domain, in the first order domain. You can think of the quantum permutation as swapping things around as a map on the domain of properties. So those who are kind of familiar with this kind of type hierarchy, so you have things that are monadic properties and things built from monadic properties. You can swap those around and get a different complete qualitative profile, at least something that's possibly a different qualitative profile. And the basic upshot of this talk was that doing a first order commutation of the first order domain, things that would take me to a poached egg, for example, just isn't the same thing as changing properties. Now, that might sometimes align in special cases, and those are interesting cases, and especially once you impose the simulation postulate, there might be a certain association with the available properties, physically available properties, the physically possible states, and the kinds of computations you can do. But those are special cases, and in any case, don't quite license some of the radical conclusions that have been drawn. So that's the general idea, and the moving part in kind of cleaving these, the key move in cleaving these apart is precisely what you mentioned, that there was a certain technical property of state formation, property formation, which is the linear combination operation, which breaks that association between these two things.
Great, thank you.
Thank you.
Axel?
And gracias. Thank you also. I hope this is not restating Oliver's worry, but maybe it's also again because I do the metaphysics part, and so that variation makes a lot of sense to me. But I don't understand why. What does quantum permutation do for physics? Because it is such a strange decision to just variate those first level things instead of having the same kind of permutations that seem so natural, at least maybe because we are just, I am just used to the kind of permutations that we use in metaphysics. So it is such a strange permutation that I am still wondering why it would be fruitful in any sense, but in particular for physics.
I think that's a really good question. I'm not so sure I can give you a definite response. I think the most unsatisfying thing that might ultimately be true is that it's just something that's really worked well and it's given us excellent predictions. And that's so kind of looking at how states behave under this what I've argued is an alien kind of permutation, the quantum permutation, is something that has allowed us to say all these interesting things that have checked out in experiment. The slightly less dissatisfying thing that I might say is that there is, of course, a very natural thought behind the definition of a quantum permutation that is informed by the idea that's behind a qualitative isomorphism. Qualitative isomorphism is the metaphysically familiar thing, right? And that's precisely when we look at these factorizable states that do correspond to conjunctions, in which case swapping the properties just is swapping the things. And now it's just the feature of quantum mechanics that there are more general states than factorizable ones, which of course we also have excellent empirical evidence for, right? And it is a certain rule, the kind of internal consistency rules of the formalism of quantum mechanics are just different than the ones we're familiar with from just first order logic, where we have this other way of building states from other states, right? And that's where we, right, and this is again kind of restating what I've said a couple of times, I guess, that's where we get some funkiness, namely that these ways of mapping properties to one another is not the same thing as mapping individuals to one another. Again, I'm not super sure how satisfying that is going to be, but I think the key thing to realize is that the motivation behind both definitions is kind of the same, right? Ultimately, you want to understand how does the general truth about the system change if I do a permutation. It's just that if you ask that in the quantumly way, you get a different response than when you ask it in a metaphysics-y way.
Okay, thank you.
Is there anyone else who wants to ask a question? Then I guess I'll ask one. So, I mean, one preliminary thing that I wanted to mention, and this is not really aimed at you, but to the whole debate, is that you were thinking of haecceitism in terms of worlds and mappings on individuals. But there is a paper by Brett Scow who argues that that's the wrong way of catching haecceitism because you will get non-equivalent formulations depending on your metaphysics of worlds. And so the only metaphysically unbiased formulation has to be in purely model terms, like with model operators and stuff. So, I mean, obviously, you know, it's not your fault. That's how the debate is cashed out. But it would be interesting to see whether there will be any difference in that respect, given a purely model definition of haecceitism.
Right. So something like if this complete qualitative profile is instantiated, say, by these individuals, then it is necessarily instantiated by these individuals. There will be anti-haecceitism, and the denial of that would be haecceitism, right? Like that's what I wanted to do.
Yeah.
I think that lots of, I mean, this seems just straightforwardly right, that it depends a lot on how you conceive of worlds. I couldn't tell you in detail, but I'm pretty sure that this conception would be in kind of rough waters when you have a Lewisian understanding, where individuals are well-bound. So it kind of, that kind of way, it doesn't even get off the ground, right? Because you just can't, unless, of course, and then the whole machinery of counterpart relations comes in. It's not quite obvious, and also he has non-standard, in at least from a certain perspective, non-standard view of haecceitism. But I think so. Of course, I've chosen this because it's very close to the conception developed and taken as the basis by Colton and some other people in the literature and philosophy of physics. But I feel like the basic lesson is something that we could also formulate in purely modal terms, though it would make it a bit more awkward because physics just straightforwardly comes with quantification of something that looks like a possible entity, namely states. I've yet to see a formulation of a state space framework in which quantification of the states has been replaced by modal operators. That would be difficult, at least in part because you have rich structure on state space, and understanding all of that structure in terms of modal operators. I mean, let's do it, right? Like, that sounds really, really cool, but I don't think we've actually done it yet.
And another thing I wanted to ask, and this is like kind of naive, Can you go back to the slide that says, but for generic state, quantum permutations are not qualitative isomorphisms, which is the main slide, essentially.
Yeah, it's this one.
Yeah. So maybe I'm just nitpicking, but when we have X and the following one, they're not really well-formed formulas, because in order to predicate something of A and B, that needs to be a predicate with some free variables, or you would have to have like some abstraction that says lambda x, y. So my issue is the following. That
Oh, the A and B's are kind of...
because, you know, when you do the... So this would be the qualitative isomorphism of this, right?
That's right.
So the way I would start is like, I have this, right, which is my state.
Yes.
Then I abstract away, I do lambda xy of xy, ab. Okay, then I swap these two. And then I do lambda reduction, and I go back to like this. That's all you have. Like, I don't see what the swapping of these two does here. So that I find that confusing, you know.
Right, I think the confusion is because the A's and B's look like variables, but like as in there is an occurrence of A, but it really is just a quick summary of facts about which of those belongs to which particle, which supervene entirely on the order in the arguments and the order in the tensor product. So in a sense, all of this works completely when you drop all the indices.
Wait, this A and B is not the same A and B as this?
Now that's a first order variable. There is a first order thing that differentiates something. That's not a...
So this A is not the same term as that?
That's not a term at all. That's just...
Well, I know what you mean, but this is the language it is. So I was just assuming that
I see what you're saying.
This was like an anaphora to this A and this B to this B, but that's not the case, right?
Anaphora?
Like that this refers to the same thing as this B does. But that's not the case.
These A's and B's don't refer to anything. They just say...
Yeah, I mean, I know what you mean. But I'm just trying to put it like semantic elements, and it's just a syntactic observation. This A is not the same type as this A.
Yes. I mean, I think if you're putting a finger on something that I think I need to be a lot clearer on, and I think that's great, because in a sense, I'm not being particularly, upfront about what syntactically is going on with these A's and B's.
Yeah.
I think that's really the point, right? Also, I don't want to say these are terms of any kind, because then there is a kind of compositionality questions and what, do I externally quantify out? Is that something I can do? Like, what happens with that, right? So that's a question that I think is good to address. For present purposes, none of this should affect what's going on here. Because all of this you can write down without even mentioning the subscripts.
Yeah, I mean, I agree with the points. I mean, I know what you're saying, and I agree with the conclusions. I just find the notation confusing because of these guys here.
Right.
Okay, so the way in which I would write it is like, I have just this state, which is of the form RAB. Okay, and then I abstract away, I do something like this. Okay, then I do this. I do the swapping.
Yes.
And then I do lambda reduction and end up with this, which would be just swapping A and B in the equation, which is precisely what we did here.
Right. I mean,
so A and B don't play any role.
In a sense, this would, I mean, from what qualitative isomorphism does, that's just unnecessary, right? You don't need to proceed through lambda abstraction. And certainly not because I did it just to show when you need these houses like that. Like you need them out when you do the lambda abstraction. But yeah, you can just avoid this. Is already in a sense, this is already in the right form, right? Because you only have a dyadic relation in a sense here. That's all it is, right? And it is labeled in a certain way. And again, you're right. It's a bit strange to have these crop up, right? But for this, that's completely, it seems to me, besides the point. Because you know exactly what you do when you replace this, right? And again, this is a confusing way to write it, because do I have another term here that I'm replacing when I do the qualitative? No, you're not. You don't, right? All you have is a dyadic property, and you replace the A's with the B and the B with the A. It's exactly what you wrote, except that I don't include this.
Yes, it's also nasty there, but yeah.
I mean, I think that abstraction comes in at some point, mainly when you talk about what the logic of the conjunction operation is. And I don't think I was actually giving you all the details here, because this kind of thing is really just a lambda abstracted expression, right, which I said earlier. And of course, for that to be a well-formed operation on the states, it needs to have another conjunct which says that they are distinct, right? The adic state can't be essential, but the same thing. So that's really, if it's a single particle states, that's the adic state that you build from it using conjunction. So that's the kind of thing where you have, sorry, there should be an X and a Y here. So that's the kind of thing that you get. It's it just means that basically these are the variables that can be filled by things, and the things should be distinct. Thanks.
We still have room for some more questions, if any. It's like not. Okay, then let's thank David. Vemos todos.
Great audio visual as well.